These last two examples are going to be a little bit more similar to the types that we're going to do in our application with Riemann sums in Unit 4. Okay, so I wanted to make sure that everyone was on board with how these were working. So you notice these are a little bit different because instead of having an index that goes from a constant to another constant, both of them are going from 1 to n. So we're still using those same series formulas, the constant series, linear series, quadratic series. We need to make sure we know those. But we're doing those in terms of just n, okay? The other thing is that this one has an a in it, okay? Meaning that since a is not the index, the variable of the index, a is operating just like a constant, okay? So the first thing I'm going to do here is use properties of the summations to split this into two different sums. So I can write this as the sum from I equals 1 to n of ai squared minus the sum from I equals 1 to n of 4a, okay? And then the other thing, which these two steps could be done at once, but I'm writing them out as two different steps for the first example, is anything that is not the variable in the index, so anything that does not involve an I can be factored to the front, okay, because it's just a coefficient. So for this one, I'm going to move the a to the front, and for this one, I'm going to move 4a to the front. So I'll have a times the sum from I equals 1 to n of I squared minus 4a times the sum from 1 to n of, and then there's just a 1 left over here. It doesn't cancel out. I still have a 1 left over, okay? And so now this part right here is the quadratic series, and this part right here is the constant series. So now I'm going to use those formulas, okay? So I still have an a in front, and then the formula for the quadratic series is the sum from 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6, okay? And then minus 4a times, and then the constant series, sum from 1 to n of 1 is just n. So these are in terms of n, and that is fine because we have an n up here. In the context of the calculus that we're going to be doing, these will be written in terms of n as well. So as far as continuing from here, really we just have some algebra simplifying to do. So I'm going to leave the an out front over here and multiply those together and see if there's anything that I can reduce or combine. So we have 2n squared plus 3n plus 1. All of that is over 6, then minus 4an, okay? And then I can see that if I were distributing, I actually would have an an that could be combined there. So I'm going to split this into three terms. The first one is 2, so an times 2n squared over 6. The 2 is going to reduce, and I end up with an cubed over 3. Okay, so that's the first term. And then we have 3n times an over 6. The 3 and the 6 will reduce, and so we have an squared over 2. And then the last term is an over 6. All right, I'll go ahead and write this in two steps. So an over 6 minus 4an, which is 24an over 6 to get a common denominator. So we end up with an cubed over 3 plus an squared over 2, and then minus, so 1/6 minus 24/6 is negative 23/6, so 23an over 6. And that is as much as we can do with that one. For this last one, move it down a little bit here. For this last one, again, we have variables on the inside other than the index. We're going to use the properties. Now here, this n happens to be the same as that n, and that, again, is totally fine, okay? So first of all, I'm going to do the two steps up here that I did together as one. So I'm going to split this as two different sums, and I'm also going to factor anything that is not the I, okay, the index variable, to the front. So we end up with 2 over n squared times the sum from 1 to n of I squared, so that would be the quadratic series, plus 3 over n times the sum from 1 to n of I, so that's the linear series. Okay, and yes, this is a variable. Yes, it happens to be the same as that, but again, in the index here, since the index is I, this n is operating as a constant. Okay, so then using our series formulas, we have 2 over n squared times, and then this is n times n plus 1 times 2n plus 1. This is going to come up quite a bit since whenever we have a quadratic series. So if you want to go ahead and just jump straight to 2n squared plus 3n plus 1, that's fine, okay? Because that would be the next step anyway. And then plus 3 over n times a linear series, which is n times n plus 1 over 2, okay? And so now we are algebrating. Let's see, we can cancel out a 2 and from both of these. We can also get rid of one of these n's. And again, this is 2n squared plus 3n plus 1. And over here, we can cancel out an n. Okay, so trying to make this as simple as possible. I've got just a 1 over n left here, and I'm distributing it to the 2n squared plus 3n plus 1 all over 3. So 2n squared over 3 times 1 over n is 2n squared over 3n. And yes, one of those n's will reduce. Okay. And then 3n over 3 times n. Well, the 3's cancel, so we just have n over n, which those will also reduce. I'm leaving them there on purpose for now. And then the last term, we have 1 over 3 times 1 over n, so 1 over 3n, nothing to reduce there. Okay, and then over here, continuing to distribute, so we have 3 times n over 2, so 3n, there we go, over 2, plus 3 times 1 over 2, so 3 halves. Okay, I do have a little bit more reducing that I can do, and a couple like terms I think that can be combined. So let's get rid of one of these n's and reduce this to a 1. And okay, so we've got 2n over 3 plus 1 over 3n plus 3n over 2. Okay, so those can combine, and then another 3 over 2. So my n terms are going to be 2/3, switch colors here. So 2/3 plus 3 halves, so let's make that 4 over 6 plus 9 over 6 is 13 over 6. So 13n over 6, that's these two terms. And then we have a constant of 1 plus 3 halves, so that's 5 halves. So that's this constant. And then we have a 1 over 3n left over. Okay, and this is as much as we can do. And just to give you an idea of where we're going, we will have a limit on all of this. Okay, we're going to have the limit as n approaches infinity. So, which is in section 1.5 in the book if you need to look back at it. But remember that the idea is we don't want n's in the numerator, because n approaching infinity in the numerator just goes to infinity. So this one would actually be infinity. But n's in the denominator are fine because 1 over infinity approaches 0. Okay, so just to give you an idea where this is going, we're going to have this in the context of a limit.